Welcome all. Today we will be solving another problem from TIFR 2019. So this question actually tackles with the understanding of principal ideal domains. So for people who do not know what principal ideal domain is, so it's practically an integral domain where every ideal is generated by a single element. Now, there are certain things that you need to understand to solve this problem, especially these three things. And first, I will mention those, and then we will see how we are actually solving these problems. So, the first thing is that if R is a commutative ring with unity, then R mod I, the quotient ring, is an integral domain. If and only if I is a prime ideal. Okay. So by prime ideal, what do we mean by prime ideal? So by prime ideal, what we mean by is that if A into B is inside the ideal, that is if A into B is in I, then either A or B has to be in I. Okay. So this is the first thing that is needed. It is absolutely essential. The second thing is that if 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 F is a field, then Fx is always a PID. That is the principal ideal domain. Okay. So if F is a field, then Fx is always a PID. Lastly, every prime ideal is maximal in a PID. So we know that every maximal ideal is prime because if I take for any commutative ring with unity, if I take a maximal ideal and if I take R mod M, that maximal ideal, it gives me a field which is essentially any integral domain. So M implies, so maximal implies prime, but prime implies maximal. This is a rare case, and it holds for a large number of rings, which are actually known as principal ideal domains. So now, how do we use these three facts? So to use the last fact, so let's say to use this, the third one, the first observation that you have to make here is something like this, that every maximal ideal is generated by an irreducible polynomial. Okay, so whenever we talk about a maximal ideal in, let's say, fx, so now we know that fx is a PID. So if I take any maximal ideal in fx, then it has to be generated by an irreducible polynomial. Okay, so all maximal ideal looks like this, where f is irreducible. This implies all prime ideals also has to look like this, where f is irreducible. Now irreducibility comes, the definition of irreducibility is something that you can understand by not making it, not taking a factorization of the polynomial. That's how irreducibility works. So if there's a factorization of the polynomial, then one of the factor has to be an unit. That is the definition of irreducibility. So here, now let us get back to our problem. So here we need to understand, is this an integral domain? Okay, so now if you look at the remarks that have been made, so R is a complete ring with unity. So if and only if I is a prime ideal, so we need to prove that, is this an integral domain? So if we want to prove this, that is this an integral domain, then what do I want to show? I want to show that, so then to show x to the power 5 plus x minus 3 is a prime ideal, prime ideal of Rx. Okay, so now, so R is a field itself. So since R is a field, Rx is a PID. So that means what we need to show is that x to the power 5 plus x minus 3 is a maximal ideal, which implies that it is sufficient to show x to the power 5 plus x minus 3 is irreducible. Right, so this is what we can have step by step if I am actually following through these steps in the first slide. Now if you look at, let's take f of x equals to x to the power 5 plus x minus 3. So if you, since this is polynomial, it is differentiable, so you have 5x to the power 4 plus 1. So as you can see that if you define your function from R to R, your f prime of x is strictly greater than 0. Okay, so since we are in the real polynomial setup, so if I define the function from R to R, then it is strictly greater than 0, which implies that f is strictly increasing, which in turns imply that f has a real root, let's say alpha. Because if you have a strictly increasing continuous function defined from R to R, then it has exactly one real root. Okay, so let's call it as alpha, then x to the power 5 plus x minus 3, you can actually write it as some x minus alpha into gx. So the moment you write it like this, then what you have actually proved, you have actually proved that x to the power 5 plus x minus 3 is not irreducible, which implies plus x minus 3 is not prime. Thus you find a contradiction in here. Okay, so all of these that I have actually taken here, these are all if and only if statement. Okay, so like I mean, if so sufficient to show this is irreducibility, so if it is irreducible, then of course it is maximal, and for PID it is an if and only if condition. Okay, so for PID every maximal idea is generated by an irreducible polynomial. This thing actually holds, and also every irreducible polynomial generates the maximal ideal. So it is if and only if statement for the PID. Hence, the moment we prove that this polynomial is indeed reducible, it's not irreducible, the ideal generated by this does not become a prime ideal. So the moment it does not become a prime ideal is the moment you get your contradiction, because for R mod I to be an integral domain, I has to be a prime ideal. So hence this statement is false. Okay, so thanks for joining. We will meet with another problem in our upcoming sessions. Thank you.